there are 6 children and 4 schools within reach. There are 6 children and 4 schools within reach. In how many ways children can be sent to schools? Try this problem. Okay. There are 6 children and 4 schools within reach. In how many ways children can be sent to schools? Now, in terms of schools and children, let us understand. Each child can go to only one school, right? A child cannot study in 2 or 3 schools. A child can go to only one school. So, capacity of each child is just 1. How many children are there? 6 children. What about school? Does school take only one admission? No, it takes many admissions. So, here there are 6 children. It can accommodate all 6. School can accommodate all these 6 children. There are 4 schools. It looks like there are just 4 schools, but the capacity here is more. So this is where my logic will work out better. So you have to treat with respect to where the capacity is less. Capacity is less with respect to children. So consider first child, second child, third child, fourth child, fifth child, sixth child. First child can go to any of the 4 schools in 4 ways. Second child can go to, for each of those possibilities, second child for each. Second child can go to any of the 4 schools in 4 ways. For each of those possibilities, third child can go in 4 ways. For each of those possibilities, fourth child. These are the total number of ways. Let us slightly twist the problem. Try this problem. Okay. There are 6 children and 4 schools within reach. In how many ways children can be sent to school such that no 2 students go to the same school? No 2 students should go to the same school. That means in a school there can be a maximum of any one of these 6 children. 1. Maximum 1. Now if you look at the capacities, children capacities does not change. School capacity, yes, it changes. Earlier school could accommodate all 6. Now no 2 children should go to same school. That means school capacity drops down to drastically 1. So you have to treat the problem with respect to schools. First school, second school, third, fourth. First school can accommodate any of the 6 children in 6 ways. For each of those possibilities, for each. Second school can accommodate any of the remaining 5. For each of those possibilities, third school can accommodate any of the remaining 4. For each of those possibilities, fourth school can accommodate any of the remaining 3. Also, as I said, individual capacity is 1. There's one more way in which you can do. Let us get back to 5 gents and 4 ladies. Are there in a party? All ladies would like to sit together. In how many ways all people can be seated in a row? Try this problem. Okay. All ladies would like to sit together. 1, 2, 3, 4, 5, 6, 7, 8, 9. If all ladies would like to sit together, there are 4 ladies. Let us say 1, 2, 3, 4. These 4 chairs are tied, or rather you consider this is a sofa which can accommodate 4 seats, right? Now think of how many items are there. 1, 2, 3, 4, 5, 6. You consider only one combination. Let us say gents sit on chairs, ladies sit in sofa. Now you interchange chairs with sofas. So 6 items can be interchanged in 6 factorial ways. By the way, whenever you come across seated, you can also get clue that it is arrangement. Okay. Also, in each of those 6 interchanges, I have not interchanged these chairs, right? I considered it as a sofa. That means I cannot plug this and put here. But then what I can consider is, ladies are sitting together, but they can interchange, they can shuffle their positions, right? And in each of 6 factorial ways, ladies can shuffle among themselves in 4 factorial ways. So in each of those 6 factorial arrangements, ladies can shuffle in 4 factorial arrangements. Therefore, total arrangements I said for each, therefore 6 factorial into 4 factorial. That's the answer. So going by this model, let us consider one more problem. There are 6 books on economics, 5 books on accountancy, and 4 books on physics. In how many ways books can be placed in a shelf? Try this problem. This question is a bit tricky because I mentioned 6 books on economics, 5 books on accountancy, 4 books on physics. I just asked in how many ways they can be placed in a shelf. I did not ask you that books on economics should be placed separately, books on economics, accountancy should be placed separately, books on physics should be placed separately, right? So in short, it is 6 plus 5 plus 4, 11. 11 books can be placed in a shelf in 11 factorial ways, right? Some of you must have definitely got it right. Now let us change the question such that books on the same subject are to be placed together Now this cannot be done in 11 factorial ways. Now books on the subject are to be placed together. Let us say you consider books on economics, books on accountancy, books on physics. Let us consider these three bags. These three as bags, right? Wherein you keep economics books here, accountancy books here, physics books here. So these three bags can be shuffled in how many ways? 3 factorial ways. In each of those 3 factorial ways, books, 6 books in economics can be shuffled among themselves in 6 factorial ways. Books on physics can be shuffled among themselves in 4 factorial ways. Books on accountancy can be shuffled among themselves in 5 factorial ways. Therefore, the answer is 3 factorial into 4 factorial into 5 factorial into 6 factorial. Let us consider next model. Again with respect to 5 gents and 4 ladies. In how many ways they can be seated in a row such that no 2 ladies and no 2 gents sit together. No 2 gents sit together. No 2 ladies sit together. Try this problem. No two gents and no two ladies sit together. If you take this case, let us look at combination. No two gents should sit together, no two ladies should sit together. One, two, three, four, five. 1, 2, 3, 4. This is how you can get the combination, right? Now, how many positions are allocated for gents? 5 positions. 5 positions, 5 gents. In how many ways they can be seated? 5 factorial ways. How many positions are allocated for ladies? 1, 2, 3, 4. 4 positions, 4 ladies. In how many ways they can be seated? 4 factorial ways. So 5 factorial into 4 factorial is the answer for the first case. Next, no two gents sit together. No two gents sit together. For this, no two gents sit together. Now, if you have to consider this scenario, no two gents sit together. For which, let us first make ladies sit with gaps on the left and right hand side. One, 2, 3, 4, 5. Okay. Now, how many positions are there for ladies? 4 ladies, 4 positions, 4 factorial ways. Now, how many positions are there for gents? 1, 2, 3, 4, 5. 5 positions, 5 gents, 5 factorial. So, the answer is not different when you compare the first case with second case. But is it the same for the third case as well? That's a question. By the way, what is the logic we have used for the second case? If no two gents sit together, let us make ladies sit with gaps in between. Similarly, if no two ladies would like to sit together, then let us make gents sit with gaps on left and right hand side. One, two, three, four, 5. So 5 gents, 5 positions. So they can be seated in 5 factorials happily. Now, how many ladies are there? Just 4 ladies. How many positions are there? 1, 2, 3, 4, 5, 6 positions. 6 positions, 4 ladies. In how many they can be seated? First lady can sit in any of the 6 positions in 6 ways. Second lady can sit in any of the remaining in 5 ways. Third lady 4, fourth lady 3. Or in other words, it is 6p4. By the way, you might be wondering what will happen to that position which is not occupied. Let us say this position is not occupied. Then what will happen? It is like 2 gents are sitting together. It's okay, right? No, ladies should not sit together. Gents can sit, right? That's what I'm talking about. So 5 factorial into 6p4 is the answer. Find rank of the word rank if letters of the word are jumbled and each possibility is arranged in alphabetical order. Try this problem. Okay. Find rank of the word rank if letters of the word are jumbled and each possibility is arranged in alphabetical order, which means if you arrange in alphabetical order, it will start with A. You don't need to worry about what are the different possibilities. How many words that start with A? 4-letter word. All are different. 4 factorial. Next, followed by the alphabetical order A, B, C, D, E, F, G, H, I, E, F, G, H, I, J, K, followed by N, right? 4 factorial possibilities. N, 4 factorial possibilities, followed by R. Now with R, you have to be a bit more careful because rank starts with R. With R, A, what are the possibilities? Alphabetical order will be this R, A, K, N, followed by R, A, N, K, right? So adding all this, you will get the word rank of the word rank. So 4 factorial, 4 into 3 into 2. By the way, 4 factorial is not correct. If we consider all the different possibilities, it is 4 factorial. Now 3 letters, 3 positions, 3 factorial, 3 factorial, 3 factorial, right? 4 factorial is the total number of possibilities, right? So there are 24 ways in which you can jumble letters of the word rank, right? By the way, here 6 plus 6 plus 6, 18, 18 plus 20. 20 is the rank of the word rank, Find the number of ways of shuffling letters of the word. We take some cases. First case, jade. Second case, jaded. Third case, Jadeja. Try this problem. First one should be very simple. J, A, D, E, all are different letters. Therefore, letters can be shuffled among themselves in 4 factorial ways. Whereas here, these two D's are similar, right? Now, if these two D's are similar, let us consider this D is replaced by this D. So, what do you get? Once again, J, A, D, A, D. So, what do you understand? So, shuffling these two D's doesn't make difference, right? Or in other words, had this been, let us say, something called as CED, JACED. If you shuffle, if you will get it as JACED, you interchange this C with this D, you get JADEC, right? You can differentiate. You can differentiate these two words. You can distinguish these two words, right? So, let us consider a scenario similar, different. If they are different, two letters, right? You will treat them as 2 factorial ways, right? Now, how many ways you can shuffle these two? 2 factorial ways. If they are similar, you will treat them as just one. right? If they are different, the total number of possibilities are how much? Assuming these two are different, 1, 2, 3, 4, 5 factorial ways. Then if they're similar, these two D's are similar, then what are the different total number of possibilities? It is 2 factorial. So what are we doing? So in the numerator, we are assuming that all are different. Then in the denominator, we are considering arrangements of similar letters or similar ones. Now using the same logic, what should be the answer here? For this, the answer is 5 factorial by 2 factorial. Now numerator 1, 2, 3, 4, 5, 6, assuming all different, it has to be 6 factorial. Now if you observe, there are 2 A's, therefore 2 factorial arrangements. Similarly, there are 2 J's, 2 factorial arrangements. That will be the answer. So far we have considered all the different possibilities of linear arrangements. So after the break, we will be considering the different possibilities of circular arrangements. By the way, before proceeding, let us consider what is the subtle difference. A, B, C, if they are linear, and A, B, C if they are circular. Let us take a break. After break, we will be discussing this.